Hello friends, in the past few lectures we've been considering what tensors are and the way of representing them, or what we refer to as the tensor notations. Now if you could recollect the way we got into the aspect of tensor, the model or the module on tensor, the way we got into it was considering two coordinate system, and we were trying to express a relation between these coordinate system that led us to rather a convoluted function and also a set of partial differential equations. We saw that using a specific form of a notation we can rather simplify or express these combination of expressions using a simple formulation, using a simple relation, and that is how we got introduced to the tensor notations. Now in the previous few lectures we saw that these tensor notation, when we express a quantity using a tensor notation, what we ended up having is representing that particular quantity as a tensor. Now by way of introducing into, or by way of getting into the tensor, we saw that the PDEs that we considered when we related to coordinate system, it yielded us, or it led us to what we now refer to as the Kronecker delta. And this Kronecker delta, it is rather expressed by using two indices I and j, and these two indices can also be expressed not as top and bottom but also as the adjacent indexes. And these indices, rather depending on the value assumed by these indices, depending on the nature of these indices, the value assumed by the Kronecker delta would vary. If these indices are identical, the Kronecker delta would assume a value of 1. If not, it would assume the value of 0. So what essentially is possible for us is, depending on the value associated with I and j, it is possible for us to come up with the different combination of the Kronecker delta. So it can be delta 1 2, delta 1 3, depending on the values assumed by the indices I and j. We can come up with the different combinations of the subscripts 1 1, 1 2, so on and so forth. And often, since we are restricted to, or we actually focus on the three-dimensional system, particularly when I and j are the coordinate axes of a coordinate system and we are considering a three-dimensional system, often there are 3 values assumed by I and 3 values assumed by j, and combination of these leads us to 9 different entities, such as delta 1 1, 1 2, so on and so forth. We have 9 different entities, and owing to the nature of the subscript, we are able to rather express it, this different values of delta, this different variations of delta, in the form of a matrix. However, when you look closely, depending on the value of I and j, when you fix the value of I and j within this matrix, delta ij would then represent a specific element. It will not represent the whole of the matrix, but within this matrix, when you fix I and j, it represents an element within this matrix. That is, when you consider a three-dimensional system, within this 3 cross 3 matrix, when you fix I and j, delta ij will then represent a specific element within the matrix. Now we consider the generalized way of expressing a generalized parameter, a generalized quantity that is similar to that of Kronecker delta, which is dependent on the value of which varies with I and j, value of which varies with the direction or the coordinate axis, couple of coordinate axis, couple of directions, and this what we refer to as the tensor. So initially this is what we refer to as the tensor, and this is how we distinguished tensor from that of a vector. So we started off with Kronecker delta. It gave us a motivation, and we generalized that Kronecker delta, and we arrived at Aij, and this we refer to as the tensor. While a vector, say for instance a vector, is dependent on a specific direction, we saw that a tensor is dependent on 2 different directions or 2 different coordinate systems. So depending on the values assumed by I and j, the value of this particular quantity, the tensor quantity A, would vary. Now towards the end of the previous lecture, we saw that this is just one form of a tensor, and this is just a second order tensor. Even though this allowed us to get introduced to tensor, but this is not the tensor alone. This is just one form of a tensor. And when I say a tensor is a parameter, a quantity that depends on 2 indices, 2 different directions, or 2 different axes of a coordinate systems, what we are talking essentially is about one particular category of the tensors, that is second order tensor. So what it essentially means is, there are also third order tensor which can be represented by I, j, k, fourth order tensor which can be represented by I, j, k and n, and so on and so forth. It is possible for us to have nth order tensors. So tensors are not always restricted to, or they do not always begin with 2, and they are not restricted to 2 alone. They can begin with 0 and they can extend all the way up to n. So when we see that there is a 0th order tensor, we saw in our previous lecture, that 0th order tensor is rather a quantity that is independent of any direction. So that means what we are talking about is essentially a scalar. And the same way when we consider a first order tensor. So first order tensor, then it depends on a specific direction. It is dependent on one index. So ai, this is nothing but a vector. So that's the reason why we are able to express. So when we consider the second order tensor in 3 dimension, we express it as 3 cross 3 matrix. And when we consider the first order tensor, for instance in 3 dimension, it will be 3 cross 1 matrix, and this is nothing but a column vector, a column representation of the vector. So ultimately what we have then is, when we consider, or the vector can also be rather represented as or can also be treated as a tensor. So whenever we write a vector as a column matrix, so when we are writing a vector as a column matrix, say A1, A2 and A3, what essentially we are doing is we are representing it rather in the form of the matrix representation of a tensor, and this vector notation is nothing but the first order tensor. So what essentially we have seen is, if you want to rather sum it all up, it can easily be summarized in this way. So we have a separate sphere of quantities that we refer to as the scalar. We have a separate sphere of quantities that we refer to as the vector, and tensor rather encompasses both. And again, when we say that a tensor is a quantity that is dependent on 2 different direction or 2 different coordinate axes, combination of it, what we are essentially talking about is the second order tensor. So that is something that we have to be very sure about. So it is just the way of getting into what a tensor is. We came up with this description. We wanted to find a way to get into the tensor, so that's the reason why we came up with this description. But again, this is rather restricted to second order tensor. If you go by the definition, even scalar is a tensor, so it is a 0th order tensor. Now let us go back to the benefits of the tensor notation, how it enabled us to rather simplify the way of expressing things, or the way of rather simplifying or writing down a set of expressions. Now in order to do that, let us begin by considering a 3 cross 3 matrix, say A. Let us consider a 3 cross 3 matrix. I have 2 lines on the bottom of the variable to represent it to be a matrix. So let us consider a matrix A. We have 2 lines at the bottom, and its element are A11, A12, A13, A21, A22, A23, A31, A32 and A33. Let us consider another matrix, similar 3 cross 3 matrix. So it will be B11, B12, B13, B21, B22, B23, B31, B32 and B33. Now let us say that the product of these 2 matrices, that is A matrix and B matrix, the product of these 2 matrices is equal to a C matrix that is represented by C11, C12, C13, C1, C22, C23, C31, C32 and C33. Now let us begin by considering. So what we have is, we have built 2 matrices, A matrix, 3 cross 3 matrix, B 3 cross 3 matrix, and C is the product of these 2 matrices, and we have expressed it as another 3 cross 3 matrix. And since we know that the product of 2 3 cross 3 matrices will yield us another 3 cross 3 matrix, we have been able to write it down like this. Now let us try to rather express the value of the first element C11. Let us try to understand how we arrive at this C11, which is here. So we'll try to understand how we are able to arrive at this C11. Now again, it is rather straightforward. It is matrix multiplication. What we essentially have is A11, B11 plus A12, B21. So we are essentially multiplying and summing up first row to that of the first column. So that is how we end up having this. So A13 plus B31. So what essentially we have done is we have now evaluated C11. What essentially we have done is we have multiplied the first element of the first row to that of the first element of the first column, second element, so on and so forth, and we have arrived at this expression A11, B11, A12, B12, so on and so forth. Now what we would want to do is, it is possible for us, we don't want to as of now jump into the any convention, any notation, we will just write it as it is. What we have is, we have two indices for each of the elements, and we could see there are certain indices that are repeating. So this can be represented as summation of j that varies from 1 to 3 and a1 j b j1. I hope you are able to understand how we are able to transform this expression to this expression. So C11 is rather written as, we have not changed much. What we are essentially doing is we have identified the repeating indices. So these indices are rather repeating. So there should not be any multiplication sign here. So it is rather a plus sign here, is just multiplication. So these indices are repeating, and these repeating indices rather are varying with one term. When you move across the different terms, they are varying. So therefore we have introduced the summation, and we have replaced this repeating index with that of a variable. So now what we can observe is rather we have expressed these three terms as a summation, and what we do have is these two indices are the same, they are the identicals. They can be rather treated as the dummy indices. And now by introducing Einstein's convention, Einstein's summation convention, the C11 can be expressed as A1j Bj1. So by including Einstein's convention, we are able to express the first element of the matrix as A1j and Bj1, that is, we have introduced two dummy indices. Now when you consider the second term, that is C12, when you want to express, so we have now identified the first element of the product matrix, and the first element now has been expressed using the Einstein's convention. Now let us move on to C12. The C12 again can be expressed as rather A11 plus B. So it will be the product of first element of the first row to that of the first element of the second column. So it will be B12. The same way A12 plus B22. The same way A13 plus B32. So what essentially we have done is we have considered what needs to be done, or we have expressed what needs to be done. Again, these are not summations, these are products. Pardon me. So it should ideally be A11 B12 plus A12 B22 plus A13 B32. Now this is what the second element of the first row of the product matrix looks like, and this is the expression that yields it. So this is 2 and this is 3. Now in the same way, like how we have written the first element of the top row, this can also be written as 1 2 can also be written as A1j and Bj2. So we have introduced two dummy indices, or rather one dummy index, and we have introduced Einstein's summation convention, and we are able to rather represent the second element in this manner, wherein you have 1 and you have 2. So this is the dummy index, and depending on the value of the other indices, so this we have in dummy indices. So the other two indices, that is these two indices, is what we refer to as the free or the live index. So depending on the values assumed by the live index, we need or we end up having we end up expressing a separate element. Okay, so what essentially we have done is we have considered two matrices and we have considered the product of these two matrices, and we are now considering the individual element of the product matrix that it yields. Now when you consider the first element of the product matrix, it comprises of a pair of dummy indices, and now we have seen that there is a pair of also a free index. Now again, depending on the what values the free index assume, that will lead to a separate element in the product matrix. Again, depending on what values the free index or the live index assume, there will be a corresponding element in the product matrix. So here the live index have assumed the value of 1 and 2, so therefore there is a corresponding element in the product matrix. In the same way, if the live index, if they assume the value of 2 and 3, say for instance through j and rather j3, then essentially the corresponding element that we will be talking about will be 2, 3. Again, if you could see the trend, if I want to talk about say an element 1, 3 in the product matrix, the corresponding expression that yields the Einstein's convention expression that yields will be 1j and bj3. Again, these two are dummy indices, and the first two indices are the live ones or the free ones, and depending on what values they assume, we are talking about a separate index. And the dummy indices, they just talk about the summation, but the live ones, they talk about rather a separate element in the matrix. Again, to ensure that you have understood or grasped it completely, let us consider an element 3,1 in the matrix. So we are considering an element 3,1 in the product matrix, and this element is again rather the product of A, 3j and B, j1. So depending on the values assumed by the live or the free matrices, we are talking about a separate entity, a separate entry in the product matrix. So ultimately, all the element of the product matrix, so all these elements of the product matrix, all these elements of the product matrix can be represented as C. So here we have used J to represent the dummy matrices, so it will no longer be involved. So Ck, so all the elements of the product matrix can be represented by Cik, where it is the product of Aij and Bjk. So all the elements of the product matrix can be represented in the simplistic manner. Again, here the Einstein's convention is involved. We should never forget that here the Einstein's convention is involved. So all the elements of the product matrix can be represented in this manner, wherein we have two dummy indices that takes care of the summation, and we have two free indices that ensures that all the different elements, all the different entries of the matrix is being represented or is being calculated. So these two I and K, these are the free indices. Again, these free indices, depending on the values they assume, they represent a different entry in the matrix. So that is what we have been looking into that far. So the entire product matrix is now being represented by this term here. So the entire matrix product, instead of expressing the entire 3x3 matrix, 3x3 matrix and the resulting 3x3 matrix, instead of writing in this manner, now the vector notation has helped us write it in a very simpler manner. So again, the vector notation, one advantage of it is rather it helps us express these matrix products in a simplistic manner, and that is what we see here. So usual way of representing, the algebraic way of representing the matrix product will be expressing the complete matrix, and the complete matrix, the product of the other two matrices that needs to be multiplied, we have to express it completely, and the third resulting product, the product of these two matrices needs to also be expressed completely. But what essentially we have now done is we have just using this tensor notation, rather we have represented the multiplication, the matrix multiplication, using a very simple expression here. Now this expression, even though it is confined to the second order, this expression here, even though it is rather confined to the second order, the dimension, the size of the matrix is rather, it can be the matrix that we consider can be any size. Again, so far we have been just considering 3 cross 3 matrix, but again, depending on what values I and k assume, the live index I and k, live indices I and k, the free indices I and k assume, we will be able to rather multiply any matrix or any matrices of any size and then able to represent it in this simplistic manner, in this elegant manner using the tensor notation. So I hope you are able to understand how rather tensor notation comes in handy when we are representing the matrix product. Now let us consider different forms of matrices and try to express them in using vector notation. Now that again, let us start with the matrix A, a 3 cross 3 matrix. So it begins with A11, A again. I don't know, my mouth hand coordination is a bit off today. So again, A13, A21, A22, A23, A31, A32 and A33. Now let us consider rather a simple column matrix. Instead of considering a 2 3 cross 3 matrix, let us consider a simple, for B matrix let us consider a simple column matrix. So it will be B1, B2 and B3. And let us try to take the product of A matrix and B matrix and let us see what it yields. So when you consider the product of this matrix to that of the A matrix, the 3 cross 2 matrix, or to that of the 3 cross 1 B matrix, a column matrix, it can be represented as A11B plus A12B2 plus A13B3. And now there is no other rows that are or columns that are involved in the B matrix, so we have to move to the next row. So it will be A21 B1 plus A22 B2 plus A23 B3. The same way, the third row, the final row of the product matrix would be A31 B1 plus A32 B2 plus A33 B3. Now this is nothing but rather a column matrix of C1, C2 and C3, and that is the product matrix. So what essentially we have done is we have taken the product of two matrices and that yields as a column matrix, and this column matrix we consider it to be C. Now let us try to rather represent the individual elements of the resulting column matrix in the way that we have done previously using the summation and then Einstein's convention and finally the tensor notation. So if you consider C1, it is equal to A11 B1, A12 B2 and A13 B3, and this can be represented as A1 or summation of j moving from 1 to 3, A1j Bj, and this is what we have as C1. Now the C2 then correspondingly would be j moving from 1 to 3, varying from 1 to 3, A23 or A2j Bj. So j, and in the same way C3, the third element of the column matrix, can be represented as, since it's just 3 elements, we can write all the 3 elements down. It will be A3j Bj. So what essentially we have is similar to that of the product between 3 cross 3 matrices. We also have in this case the product between a 3 cross 3 matrix and a column matrix. This can also be represented, the elements of the product matrix that we get can also be represented using the summation scheme. And when you use the Einstein's convention, and we have identified our dummy variables, they are j, and the dummy variables occur at, or the dummy index rather, it is a part of the column matrix and it is one of the part of the R 3 cross 3 matrix, and so the C1 can be represented as C1 j Bj, again using Einstein's convention. So only when it is explicitly stated the Einstein convention is used, only then we will be able to understand this means that. So only when Einstein's convention is, that's the reason why in every place I am writing Einstein is because only when it is stated we will be able to rather relate this to this. If not, it has a totally different meaning. So the CU1 is represented in this manner. So 1 is rather the live or the free index and j is the dummy index. So therefore Ci would be Aij Bj. So the dummy index. So when you consider this expression and compare it with what we have seen earlier for as the product of 3 cross 3 matrix, it will be what we saw in that case was Ik is Aij Bjk. So this is for the product when we had 3 cross 3 matrices. In this case it is a product. This is also the elements of a product matrix, but what essentially we have is a product of a 3 cross 3 matrix and a column matrix. So that is reflected in the number of indices associated with the second matrix here. And as you can see, just a way of understanding this product is that when you consider the product of two matrices and when you are able to identify the dummy indices, the product term is rather written off these dummy indices. Let me repeat. You are considering the product of two matrices and we are relating it to another matrix. And now you are able to identify in the two matrices that you are multiplying, when you are able to identify the dummy matrices or the dummy indices rather, these dummy indices are removed while you are expressing the product matrix. So here you have two elements of the matrix that you are multiplying, and these elements we have identified there are each of these two elements have one dummy index associated with it. So when you remove that dummy index, you are left with I and k, and that is what is the index associated with the product element. The same way, so you have identified j as the dummy index. When you remove it, you are left with I and k. In the same way here, you have the dummy index. You have identified the dummy index as j because here, here and here, here, here and here. The conventional way of representing the element of a product matrix. There you are able to replace the numbers with a variable, and that variable indicates the summation, and when you have an index that just indicates a summation, then what essentially you have is a dummy variable. So therefore when you are relating the product of the elements of two matrices and thereby relating it to an element of a product matrix, it is possible for us to just get rid of this dummy indices, and the resulting index is what will be associated with the product matrix. So here we have, if we get rid of j, the resulting index is associated with the product matrix. So if you just get rid of these two, the resulting one is I, that is what is associated with the product, the element of the product matrix. The same way we have dummy index j here. If we get rid of this two, I and k are the free index, and that is what is associated with the element of the product matrix. So that is one way. If you out of nowhere, if you find without all these introduction or without saying how we arrived at this, how we arrived at all this, if you just see an expression of this sort, say KL is the product of A HI and B I K, then you will be unable to understand what this essentially means. So if you want to write an expression for the elements of the product matrix, now you will be able to write it as the combination of the elements of the two different matrices, and just by introducing a corresponding dummy variable. You can introduce j as your dummy variable, it doesn't really matter, but what you need to understand is the index that is rather not dummy, the live index is what gets reflected in the elements of the product matrix. So just a way to understand. Now let us focus on this description here. Let us focus on this particular representation of the product of two matrices. So one is a 3 cross 3 matrix in our consideration, and other is a column matrix, and what we get out of it is also a column matrix. So Ci and Bj both are nothing but a column matrix. So both are column matrices. So what essentially we mean is Ci and Bj, they are rather two different vectors, C vectors and B vector. So what essentially we are doing, we are considering a product of a matrix and a vector, and that ultimately leads us to another vector. So in this case we are considering, so what we have done is we have considered just two vectors and we have considered the product of it. one vector, or rather we have considered two matrices and we have considered the product of these matrices. So one is a 3 cross 3 matrix, the other is a column matrix, and when we consider the product of these two matrices, we ended up having a column matrix. We ended up having a column matrix. A regular matrix, product of a column matrix, we ended up having a column matrix. And we know that, or we have seen earlier, that the column matrix is rather the representation of a vector. Particularly in this discussion on tensor, the column matrix is rather a representation of a tensor. So what essentially we have is, we have rather a tensor C that arises from, or that is we arrive at this tensor C by taking the product of the tensor, or we are taking the product of a matrix and a tensor B. So by taking the product of a matrix and a tensor B, we have arrived at, or rather by taking the product of a matrix and a vector B, we have arrived at another vector C. So what essentially we are doing is, by multiplying an existing vector B with a matrix, we have transformed the vector B to vector C. Let me repeat. We have a column matrix. This column matrix, we can refer to it as a vector. So this column matrix that we have here is a B vector. Now what we are doing is, we are multiplying this B vector. So we are taking the product of a matrix and a B vector that ultimately gives us a C vector. So essentially we are transforming the B vector to C vector by taking the product of a matrix and the B vector. So essentially this is what we refer to as the linear transformation of vector. So what essentially we have is, we have transformed B vector to C vector by taking the multiplication, or by multiplying a matrix to that of the B vector, and this is what we refer to as the linear transformation of a vector. What essentially, in the geometrical sense, what it essentially means is that when you are representing a B vector in a space, in a vector space you are representing a B vector, and you want to represent the same B vector in a different vector space, it can be of same dimension, it can be of a different dimension, then you have to transform the B vector to the new vector space, and that will be your C vector. So this transformation can be done by by multiplying it with appropriate matrix. Okay, so what essentially this expression here means, so the recent, the last matrix multiplication that we have considered, a matrix, 3 cross 3 matrix multiplied by a column, a matrix. So what essentially we are considering is a product between a matrix and rather a vector, and this transforms the vector from one vector space to another vector space. So if you, you don't have to get into the specific details of transforming, or this is referred to as mapping. We don't have to get into the specific details of it, but the bottom line we need to understand is that we are changing one vector to another vector, and depending on the nature of the matrix that you consider, the vectors might have a different scale when compared to the previous vector. The C vector is possible to have a different dimension when compared to that of the B vector. But nevertheless, what essentially we have done is, we have transformed one vector to another vector by multiplying it with a matrix and the existing vector. Now, when you represent this linear transformation of vectors using the tensor notation, we saw that it can be represented as I, A, I, J, B, J. So this is the way this linear transformation of vectors can be represented. So one vector transforming into another vector can be represented in this way. Now as you look, when you look closely, we are transforming one vector into another vector. Each of these vectors they are represented by distinct indices. So they are represented by, these are two different vectors, they are in two different vector spaces, they are represented by distinct indices. And when you want to transform one vector, that is B, to that of C, again these two are equivalent. So this is something that we need to understand. This is rather the conventional way of writing this. So this is nothing but the C vector. When you represent it, it will be a column matrix. B vector a column matrix. A is a 3 cross 3 matrix. So column matrix, 3 cross 3 matrix. So again, because we have considered 3 rows in this column, or Even in B, we have considered 3 rows in a given column, so therefore we have considered 3 cross 3. So the dimension of this matrix will depend on the nature of the matrix that we have considered, but nevertheless, the vector notation of such transformation operation of the vector, the tensor notation, the way of representing each element of the transformed vector is of this form here. The key point we need to take, or the key understanding that we need to gain here is, we have 2 vectors. We are transforming one vector to another. In order to do so, we need to have a matrix. So you are transforming one vector to another. In order to do so, you need to have a matrix. You are transforming a quantity with one index to a quantity with another index. For that, you need to have multiply or you need to involve a quantity with 2 indices. You are transforming a quantity with one index to a quantity with one index. For that to be done, you need to multiply it with a quantity of 2 indices. Now, if we extend this, so these are just tensor, rather vectors. Ci and bj, they are rather vectors. Now, if I want to have similar transformation for my tensors, which are represented, so let's assume, let us begin with the second order tensor. So we started off with the considering so far as the first order tensor, so we will move on to the second order tensor. So if I want to transform my second order tensor, then what needs to be the matrix that I need to consider. Now we have attempted to transform one first order tensor to another first order tensor. For that, I need a matrix that, or a quantity that has 2 indices associated with it. So here the vector that that is transforming has one index. It is transforming to another vector that has one index, but in order to do so, I need to multiply it with a parameter that comprises of 2 indices. Now I want to transform a tensor that has 2 indices within itself, and I have to transform this tensor to that of a tensor ij. Now I have to transform this to this. So I have seen, or we have understood how we can transform one vector to another vector, one first order tensor to another first order tensor. Now we want to transform one second order tensor to another second order tensor. I now want to map one second order tensor to another second order tensor in a specific tensorial space. Now how could I arrive at that? How can this similar expression can be extended to this? So in this case, now it is for us to realize that we need rather a tensor that is of. In this case, we are dealing with 2 first order tensors. We are transforming 2 first order tensors, and in order to do that, we need a tensor of second order. We are transforming 2 first order tensors, and in order to do that, we need a tensor of second order. In this case, 2 first order tensors are transformed, and in order to do that, we need one second order tensor. The same way, we are here trying to transform 2 second order tensors, and in order to do that, we need one fourth order tensor. So when we want to rather transform 2 second order tensors, we need one fourth order tensor. So I hope you are able to rather arrive at how this expression here. We will try to rather look deep into this fourth order tensor in some minutes, or maybe in the next lecture. But what I want you to understand is, in this case, what we are trying to do is we are trying to transform, like in the previous case, one tensor to another tensor, one second order tensor to another second order tensor. And in order to do so, what essentially we need is we need a fourth order tensor. We need to have a product of a fourth order tensor and a second order tensor in order to transform this second order tensor bkl to cij. Now when you look closely here, it is possible for us to identify the dummy variables. The same understanding here also lies. Again, for our understanding, it can be these two. When you treat these two as the dummy variables, the remaining is what is being assumed by the product element. So there is something for our understanding, but nevertheless the key point remains the same. When you want to map a first order tensor to another first order tensor, you need a second order tensor. So that is what we have, and that's why we have aij. Now on the other hand, when you want to map rather a second order tensor to that of another second order tensor, what essentially we need is a fourth order tensor. So we need to take the product between the fourth order tensor and the corresponding second order tensor. Now the reason why we are interested in the transformation of the second order tensor is because the relevance of this operation is huge in materials research, because both stress and the strain, both these are second order tensors. So when you want to have, or when you want to arrive at the stress from strain, when you want to arrive at, or when you want to reach the stress from strain, so what essentially we need to do is we need to map the corresponding values of stress in the strain space, or the strain in the stress space. Both can be done. So that is possible when we are able to do such an operation. So it means when we are trying to transform the strain to that of the stress, it needs to be multiplied by rather a fourth order tensor. And from the Hooke's law, we will now, or you can rather guess what would be the parameters, that what would be the quantities now that needs to be expressed as a fourth order tensor. So we will begin with this particular aspect. We will begin with the way of expressing the relation between stress and strain in a comprehensive manner, in a most exhaustive manner, in a more convincing manner in the subsequent lecture. But the underlying concept for expressing the stress-strain relation in a more expansive manner starts from this, wherein we would like to transform one second order tensor to another second order tensor, and that requires involvement of a fourth order tensor. So with this we will try to rather understand, with this we will try to extrapolate or reach the way of expressing the stress-strain relation in an elegant manner in the subsequent lecture. Goodbye.